Hi everybody, welcome to another video in differential equations, section 6.3, the undetermined coefficients and the annihilator method. So in this section we study a new method, a new approach to non-homogeneous equation. So first we define the annihilator. A linear operator A is set to annihilate a function if we apply to the function and it is equal to 0. So pretty much annihilator turn a function into 0, and that is a differential operator. Right. So that is A annihilate F if F is the solution of the homogeneous linear system of linear differential equation. Right. So we should give a very fundamental example. Let's say we have the function x squared plus 2x, for example. Now, if we take the derivative again and the derivative 3 times, it's going to be equal to 0, right? Because let's just write that. The first derivative is 2x plus 2. The second derivative is 2. And if we keep going, the third derivative is equal to 0. So we say the third derivative annihilate the function and turn the function to 0. So we can say d cubed, which is the third derivative, annihilate the function. Because if we apply derivative 3 times to the function, that will turn the function to 0. So that's what it is. Of course, if the third derivative is 0, the fourth derivative is also 0, and the fifth derivative is still 0. So yeah, we can still have higher order, and that still annihilate the function. Right. So this method of finding annihilators. The differential operator, so the n derivative, will annihilate everything up to the n minus 1 power of x. For example, the d cubed annihilate anything up to the second power. That certainly annihilates the 2x, of course, annihilate the x squared also. So when we have the n order derivative, or d to the n, we annihilate anything that degree 1 less than it. Right? Of course, it have to be the whole number. If it is x to the 1/2, it's not going to apply the derivative. It's not going to annihilate square root of x, so it's not going to work. I mean, of course, it's raised to the natural numbers only. Right. So d to the n annihilate all of that. D minus alpha to the n annihilate e to the alpha x, x e to the alpha x, all the way up to the n minus 1. So you notice the pattern that we'll have the power of n here. It will go up to the power of n minus 1 of x. And that will be the same thing for all of them. So when we have x to some power multiplied by either e to the alpha x or e to the alpha x cosine beta x, that means we're going to need some factor raised to the n power to annihilate. By the way we write this, because later on we will tie that to the auxiliary equation, so that will be another story. But now let's look at this example. Right. I'll find an annihilator. Of course, this is just an annihilator, because notice that if we have d cubed, we may have d to the 4th power also annihilate the same function. So annihilator is not unique. We can always increase the higher degree and still annihilate things. Right. So find an annihilator for each of these functions. So this is to the 3rd power. We need the 4th power. So easily we have to choose degree 1 more than the polynomial, the highest degree of the polynomial. So that will be d to the 4th. Right, next we have this. If we rewrite this, we have x e to the negative 2x plus 5 e to the negative 2x. Now, to annihilate this, we need d minus the exponent. So that's d plus 2. So we're going to need d plus 2 for that. We still have e to the negative 2x here, so we still need d plus 2. However, on this one, we have x to the first power. And if there's x to the first power, the annihilator must be 1 more than that. So the annihilator. So this, we annihilate this term. Yeah, d plus 2 square will annihilate this. And because d plus 2 annihilate this, suddenly d plus 2 square will annihilate this. So that's why when we put them together, we're going to use d plus 2 square. So in general, we might have a polynomial. I'm just going to give the example here, 2x squared plus 5x minus 1 plus 1, for example, and e to the negative e to the 5x for example. First, we determine what will annihilate this. So the annihilator of this will be d minus 5. And I say, where do we get that? Well, think about this. The auxiliary equation, if we have r minus 5 equal to 0, then we have r equal to 5. And from r equal to 5, we will have the solution in this form, right? So think about that in terms of auxiliary equation. In order to produce the solution of e to the 5x, we have to have r equal to 5. In order to get r equal to 5, we have to have r minus 5 equal to 0. And now we replace r by d. That is the annihilator. Now, we multiply to a polynomial of the second degree. So the second degree, to annihilate that, we're going to need degree that is 1 time bigger, 1 more. So this is the annihilator of the whole thing. Right. Next, I'll find the annihilator of this. First, when we write like this, I will, instead of give the answer in this form, I will say, how about we have 3 e to the 0x and then sine 5x. So to write like that, so we have alpha is equal to 0 and beta equal to 5. And the annihilator is d squared minus 2 alpha d, d squared minus 2 alpha d plus alpha squared plus beta squared. So that's why we put in this form. By the way, in front here we do not have any power of x. So that's why this is to the first power. If we have an x here to the first power, then we have to have the power increased by 1. Right, but we don't. So that's to the first power, and we have d squared plus 25 is the annihilator of that. Right, let's look at this example. I'll find an annihilator for this function. Right, so first, what annihilate 6x e to negative 3x? So we'll just look at one by one, right? 6x e to negative 3x. For e to negative 3x, the annihilator will be d minus negative 3 or d plus 3. In front of that, we have the power of x to the first power. So to annihilate that, we need to have the degree that is 1 more than it, 1 more than that. So the annihilator is d plus 3 square. So this is the annihilator of this term. Right. Now, next, for 3, the 3 or 6 doesn't really matter. We only worry about the term. the variable terms. Right. Now, if we write this, alpha is equal to 1 and beta is equal to 2. So let's just write 3 into alpha sine beta x. So we will have alpha equal to 1, beta equal to 2, and the annihilator for that is d square minus 2 alpha, just write it the form first, plus alpha square plus beta square. Now to the power. Notice that there's no power of x here. So in that case, we just need 1 here because there's no power of x. So we have d square minus 2, alpha is 1, alpha is 1, alpha square is 1, beta square is 2 square is 4, 1 plus 4 is 5. So we have that. So we say this annihilate that and this annihilate that. So to put them together, do we add them or what? Now remember, if we want to annihilate both of them, we're just going to multiply this. For example, because if we have e to the x and we have d minus 1 multiplied by it, it will eliminate that. If we have, let's say, sine x, the sine x, the annihilator is d squared plus 1. We annihilate that. So if we want to eliminate both, annihilate both, we just multiply them. So d minus 1 will annihilate e to the x, d plus 1, d squared plus 1 will annihilate sine x. So in that case, when we multiply together, it will take care of all of the terms for the function. So in that case, the annihilator is, we multiply this together. So d plus 3 square, and then d square minus 2d plus 5. Next, I'll find the annihilator for this annihilator for x e to the 3x. We will have d minus 3, and we have x to the first power. So we're required to have the power that is 1 more than it, which is equal to d plus 3. Sorry. Yeah. I think I just copy and paste it. So that's still d plus 3 square. Yeah, d plus 3 square will annihilate that. For sine x. Sine x. We can write that as e to the 0 x, which is 1, and then sine 1x. So alpha equal to 0, beta equal to 1. And the annihilator is in this form. There's no x here, so let's just go to the first and put that together. Put 0 here and 0 here, and we just have d squared plus 1. Now, d plus 3 squared will annihilate that. D squared plus 1 will annihilate that. If we want to annihilate both, so, and this is only one of them, so we say an annihilator is d plus 3 square d square plus 1. Notice that if I want to, I can just multiply d to the 5th here. That does not affect the annihilator. It's still annihilate the function, because after we do all the derivative, we take derivative 5 times. Derivative of 0 is still 0. So that's why we can just multiply anything to it. It doesn't affect the values. The derivative of 0 is still 0. Right. I'll find the annihilator of this. So first, to annihilate, I just say to annihilate this. To x to the 5th, we need one more degree, right? Will be d to the 6th. Yeah, for polynomial, we're going to choose one degree will be one time bigger. I mean, one more than the highest power of x. Right, now for this one, x e to the x cosine 3x. Now, let's put some numbers so it's easy to see. First I have x to the first power. E to the, now this will be 1x. So alpha is 1. And cosine 3 then x. Right. Now, ignore the x to the 1 for a moment. That will give us a square later. But alpha is 1, beta is 3. And the annihilator is d square minus 2 alpha d plus alpha square plus beta square. And in this particular, we have the x in front of it, so we'll need the degree 1 more than that. So we have a 2, the square there. Right, so we have d square. Alpha is 1, so we have 2 minus 2d plus alpha square, 1 square is 1, 3 square is 9, 1 plus 9 is 10. So that annihilate to x to the 5th, and that annihilate x e to the x cosine 3x. So put them together, the annihilator is d to the 6th d square minus 2d plus 10 square. Right. So now we know how to find the annihilator. Now, by the way, this is the annihilator in the sense is related to the auxiliary equation. All we do is just replace r by d and we have the equation. Right, now how do we use the annihilator approach for the non-homogeneous equation? So this is how we do it. First, find a complementary solution to the corresponding homogeneous equation. Because that's easy, usually that's what we do first. And then find the annihilator to convert the non-homogeneous equation to the homogeneous equation. So pretty much we'll multiply that on both sides. And then compare the original complementary solution to obtain the form of the particular solution. Right, so just on the word, let's see how it works. So first, I look at this example. I'll find the form of the particular solution to this equation. So we have that. So first, homogeneous equation, auxiliary equation for that is r squared plus 1 equal to 0. So we have r equal to plus or minus I. And because of that, we have y1 is cosine of x, y2 is sine of x, and complementary solution is this. So this should be easy. Now, for the particular solution, we will use the annihilator approach. First, to annihilate the right hand side, we're going to need d square. Right? And now the original equation, instead of writing this form, I can write d square y plus y equal to 2x plus 1. So we can factor out d square plus 1. You see, the d squared plus 1, that is exactly as the auxiliary equation, but we just replace d by r. That's simple enough. right? So that original equation written in this form. Now we multiply, or we should say we apply the annihilator on both sides. So apply this way on both sides, and that gives us 0 because that annihilate 0. Now when we have that, then this turn into an auxiliary equation. To solve for that, this is the 4th degree polynomial, so we have the solution as 0, that's the double root, plus or minus I is the other two root. So for 0 we have e to the 0 power e to the 0x, which is 1, right? And then next one we have x e to the 0x, which is x, and then cosine x and sine x, and put all of them together, we have the solution in this form. Now we will compare to the complementary solution, which have the form of sine cosine, because we have this as the complementary solution. That means the particular solution has to be in this form. That's why we have a particular solution in that form. Right. So in terms of guessing, this is just a little more systematic, but it's still just, it can only work for a certain type of input function. So if we have like tangent here, it's not going to work. We have to use variation of parameters, because we don't know what is the annihilator of tangent. I mean, it's not given in the table here, right? Right. Now, find the form of the particular solution to this non-homogeneous equation. So the first part, of course, is we're trying to find the complementary solution. I try to write small. I don't know how much space do we need here. So first, complementary solution. Right, for this one, if we want to write in the differential form, second derivative is d squared, first derivative is 2d, the function is just 1. Yeah, we can rewrite like that. Or of course we can just write the auxiliary equation. Which is exactly like this, but instead of d we have r. So if r squared plus 2r plus 1 equal to 0. Right. So from that we have r squared plus 2r plus 1 equal to 0. Of course, this if we factor. And with that we have the repeated root of -1. Right. Yeah, I don't know how long the problem will be, so I try to write small, a little more compact. Right, so we have a solution. So we have y1 is equal to e to the -1x and y2 could be the same thing, but in that case that will not be linearly independent. So we have to stick an x to it to make it linearly independent. And we have y1, y2, and so we have the complementary solution c1 y1 plus c2 x e to -x, c1 y1 c2 y2. So yes, so this is the complementary solution for homogeneous equation. Right. Now second part is the particular solution, and we used the annihilator approach. and this time we use Annihilator Approach. First, what will annihilate that? Right, so the first step, of course, the annihilator. Right, let me switch this real quick. Right, find an annihilator. To annihilate 7. We need to have the derivative of 7 is equal to 0. And to annihilate 75 sine of 2x, if we want to rewrite this as 75 e to the 0 x sine of 2 x, and then the annihilator is d square minus 2 alpha d plus a square plus b square, plus alpha square plus beta square. Right. And there's no x here, so that's just to the first power. So this way we have d square alpha 0, so we just have d square plus beta square, so d square plus 4. So we have d square plus 4 will annihilate that, and d will annihilate that, put them together, so the annihilator is d times d square plus 4. Right, so that will annihilate the whole right hand side. Now, next, we'll go back to the original equation. I'm going to write in this form. Now, we will apply this on both sides because we want to turn the right hand side too. So we multiply that on both sides. So apply this on both sides. We have d square plus 4. Yeah, with this step we apply annihilator. Yeah, we apply the annihilator on both sides. Right, we know the right hand side is equal to 0 because that's the whole point of the annihilator. On the right hand side, yeah, just leave it like that. Right. Next we have, this is an homogeneous equation, right? Yeah, so when we apply the annihilator on both sides, we should have the homogeneous equation. So So in that case, we will have the auxiliary equation. Right. So we just write that exactly the same. Instead of D, we have R. So we have R squared plus 4, R squared plus 2R plus 1 equal to 0. And then we just solve for R. R1 equal to 0. Next, R squared plus 4 equal to 0. So we have R equal to plus or minus square root of negative 4, so plus or minus 2i. That's 2 and 3. And then R squared plus 2R plus 1. We already did that actually. It is negative 1. That's a double root. So I say that's 4 and 5. It's negative 1. Right. So we have 5 solutions to the auxiliary equation. So to put them together, we can say y1 is equal to e to the 0x, which is 1. y2 for 2i we have cosine and sine, so cosine 2x. And then y3 sine of 2x. y4 e to negative x, and y to the 5th e to negative x. But because that repeated root, we'll multiply the x here, so we have linearly independent. Right, so 5 solutions, and we will have the general solution will be in this form: c1 times 1, which is just c1, and then c2 cosine 2x, c3 sine of 2x, c4 e to negative x, and c5 x e to negative x. Now we look at the form of the complementary solution we have earlier, e to negative x and x e to negative x. So this will give us the complementary solution. Because of that, what's left must be the particular solution. So because of that, what's left here will be the form of the particular solution. So we say, so particular solution will have the form of c1 plus c2 cosine 2x plus c3 sine of 2x. Nice, right? And they'll say, well, that doesn't, that's simple. We can just guess, right? That should be, just guess something, the form for the input function. Of course, we can guess, but this case is so that it is a little more systematic when we write in this form. When we do that, we have the homogeneous equation and rewrite the solution. We'll have the complementary solution, and what's left will be the particular solution. And they'll say, is that come from the annihilator? Right? And I will say yes on this one. But in general, it might not just come from the annihilator. You will see. I would look. Let's look at the next example. Right. So, find a particular solution using Annihilator Approach. I'm not sure if we have enough space to do the whole problem, but at least we have to come up to the form of the particular solution. After that, of course, when we have this, we take derivative, second derivative, and then put it back in the function. That's still undetermined coefficient. We still solve for the coefficient. When we put it back into the original equation, we can solve for it. But that's what we have. Right. Perfect. So the step is, of course, complementary solution. That's usually the case. Then find the annihilator, apply to both sides, to obtain a homogeneous equation. For that homogeneous equation, we have the new auxiliary equation, and then write the solution out. We should have the complementary solution, and we should have what left is the particular solution. Right, and the particular solution does not only come from the annihilator. Right, we'll see. Right, I'll find a particular solution using the annihilator method. Right, so same thing. First step, find the complementary solution. 1. Complementary solution. That's 4. Complementary solution. So for that we construct the auxiliary equation with r squared minus 4r plus 4. So be exactly like that. Right. Look like we can factor out. R minus 2 square. Right, r minus 2 times r minus 2 is that. So in this case we have two solutions. Repeated root of 2. So we have y1 is e to the 2x, y2 e to the 2x. We need an x for linearly independent or for the repeated root, and the complementary solution will be c1 y1 plus c2 y2. Forgot the x. So that's what we have. Complementary solution. Next, of course, we find a particular solution, and that's exactly what the question asks us to do. So particular solution. And we use Annihilator Approach. Alright, first of course we find the annihilator. To annihilate the right hand side, that's easy. That's d minus 2, pretty much. Right, so that's what we have. Right, and of course if the annihilator is d minus 2, then the particular form, if we use that, it's not going to work. Right, you will see that why it's not going to work. Right, now we'll go back to the original equation. Original equation. E squared minus 4d plus 4 times y equal to e to the 2x. Now d squared minus 4d plus 4, if we can factor, it will be like this. It will be d minus 2 square y e to the 2x. Right. Now we applied the annihilator on both sides. So we apply d minus 2 on both sides. And the annihilator will annihilate that, because so we have 0, and we will have a d minus 2 cube. So that is the homogeneous equation that we want. Now from this, of course, we write the new auxiliary equation. Be r minus 2 cubed. And we solve for that, we will have r1, 2, and 3. So this is the triple root of 2. Right? Triple root of 2. Because of that, we can say y1 is e to the 2x. y2, because of linearly independent, we multiply x to it. And y3, because of linearly independent, we multiply x squared. And because linear combination of this is new solution. C1 e to the 2x, C2 x e to the 2x, C3 x squared e to the 2x. Now, compared to what we have earlier, the complementary solution will be the first two terms. Because of that, the particular solution will have to be this form. Right? Of course, if we guess, it should be the same form. So this will be y particular. So from here we say the particular solution will be in the form of some constant. Let's just use a x squared e to the 2x. Right. What's next? If we have enough space, I will try to write small. We have the functions that we take derivative, second derivative, and use the undetermined coefficient to solve for the coefficient a. So this should be simple. Right. So what's next is the undetermined coefficient. So we start with particular solution ax squared e to the 2x. If we take derivative, it will be using a product rule. So derivative of the first times the second plus the first times derivative of the second. So give us 2ax plus 2a x squared. I just factor out those two. Just multiply it out. This may just leave it like that. And then we'll take the second derivative. This is the first derivative, by the way. Right. Again, product rule. Derivative of this 2a plus 4ax. Derivative of the first with the second plus the first with derivative of the second 2e to the 2x. Right, now once again factor out 2e to 2x. We will have 2a plus 4ax. Notice there will be a 2 that we need to multiply back in. Distributed the 2 inside. We have 4ax and 4ax squared times e to the 2x. Combine like terms. We have 2a 8 times ax plus 4ax squared e to the 2x. Right, so that is the derivative. So the function second derivative, first derivative, now substitute into the original equation. Let's just rewrite this original equation. D squared is the second derivative minus 4 times the derivative plus 4 times the function equal to e to the 2x. Right. So substitute into all of that. What colors? Now we substitute into second derivative minus 4 times the derivative, 4 times the function equal to e to the 2x. Right. Second derivative is that 2a ax plus 4ax squared e to the 2x. So that is the derivative. Then minus 4 times the derivative will be this. And then plus 4 times the function all of that will equal to the right hand side of e to the 2x. Right. Now we just combine like terms, all of the terms on the, let's factor out e to the 2x and factor it out. So what do we have? Now we use everything in blue now. 2a ax 4ax squared minus 4, don't forget there's a 4 here, minus 4 times that, so we have minus 8ax minus 8ax squared and then plus 4ax squared for that one. Yeah, I guess we can use just keep the color code if we want to. Sorry. (2a plus 8 ax plus 4ax squared, and then subtract that, and then the last one will be plus 4ax squared right. And then we have e to the 2x on the outside. Right, now to simplify, what do we have? Ax, 8ax. Now the ax squared, wait, I'm not sure where this come from, so yeah, sorry. Yeah, that's one I should write in black, and that's it. So we don't have that term, multiply 2, that's all we have. Right, now we have 4ax, and then 4ax, and then minus 8 plus 8 cancel out. So what we left is just 2a equal to e to the 2x. So because of that, a is equal to 1/2. Right. So, and particular solution is in that form. This particular solution will be 1/2 e to the 2x. Right. So in this case, it's only one coefficient to solve for, so that you know there will be a lot to simplify. And what we should have, because that cancel out everything, we just have a equal to 1/2. And so that substitute back in there. If I do that correctly, it's 1/2. There's x squared e to the 2x. Right. So as you see, the annihilator, in this case d minus 2, that does not give us the particular solution. So that's why we have to compare, put it back into the original equation, because there may be some redundancy, because some linearly independent problem, the particular solution may end up being different than what we get from the annihilator. But when we have the particular solution, the rest will be similar to what we have as before. Take on the derivative, substitute back into the original equation, and solve for the missing coefficient. In this case, only one of them, and we solve for that is 1/2. That's what we have. Right. Right. So the initial value problem. This one looked like we will not have enough space to do, but let's get the form of the particular solution. Right. So first, complementary solution. So we have auxiliary equation will come from here. Yeah, this one definitely we will not have enough space to complete the problem, and I'm not planning to do the complete problem. Just get the form of the particular solution, and we stop there. Auxiliary equation, the third derivative, r cubed minus 2r squared plus 5r equal to 0. Right. Here we can factor out r equal to, factor down r, then r squared minus 2r plus 5 equal to 0. right? Now we have r equal to 0 and the other equal to 0. So we have r1 equal to 0, and then we have the equation. Right. For this one I have to use quadratic formula. Negative b plus or minus b squared minus 4ac over 2a. So that gives us 2 plus or minus 4 square, 2 squares 4 minus 20, that minus 16 over 2. Negative inside the square root is I, square of 16 is 4. Right. Do not cancel the 2 here, that will be wrong. Have to factor out first. We can only simplify when there's a product. So we have R1, R1 ready, so R2 and 3 will be 1 plus or minus 2i. Right, so those are the solution, and from there we write y1 equal to e to the r1 x, which is 1, y2 for this one, alpha is equal to 1, beta is equal to 2. So y2 will be equal to e to the alpha x cosine beta x, y3 e to the alpha x sine beta x. So when we put them together, we have c1 times 1 plus c2 times that e to the x cosine 2x. This is the complementary solution. And c3 e to the x sine of 2x. Right, complementary solution. Second, now try to find the form of a particular solution. First we find the annihilator. That annihilate negative 24 e to the 3x. To annihilate that, we will have d minus 3. That's it. Yeah, d minus the power, the coefficient of the exponent. Right, so that's pretty much this. And now the original equation. Original equation, we write third derivative d cubed minus 2d squared plus 5d applied to y equal to negative 24 e to the 3x. Of course, if we rewrite this, we have d squared minus 2d plus 5, which is exactly as that as the auxiliary equation. But instead of R, we have D. Right. Next, we applied the annihilator on both sides. By the way, at this stage, when we see that the annihilator is different factor than what we have from the auxiliary equation or what we have from the original problem, then in this case we know the particular form will come from this. The last problem though, we have d minus 2, which is have the same factor as the original problem. So that's why we know we have to do something to it. So that's why the particular solution will not be just from d minus 2. There will be something to make it linearly independent. And this one though, d minus 3, completely different than this. So we know for sure the particular solution just comes from d minus 3. Right, so. Yeah, apply the annihilator on the right hand side. Right. For the annihilator, the number negative 24 doesn't really do anything because the coefficient does not affect anything. Right. So for all of those problems, the coefficient does not affect anything. I should have emphasized that earlier. But like that, if we have x squared and we take the third derivative to it, it will be 0. If we have 2x squared, that's still 0, right? So the coefficient doesn't really do anything to affect the annihilator. So that's why we don't really even need the negative 24. But that will annihilate and we have 0. So in this case, we just write the auxiliary equation, be the same thing, but it's R instead of D. So we have new auxiliary equation. R minus 3, R squared plus 2R plus 5 equal to 0. We already solved for this. R minus 3. So we have R minus, let's just write that out. From this we have R minus 3 equal to 0. R equal to 0. R squared plus 2R plus 5 equal to 0. So from this one we have R1 is equal to 3. R2 is equal to 0. R3 and 4 is 1 plus 2i. We already did that. Plus or minus 2i. Right. So with that we have y1 equal to e to the 3x. y2 e to the 0x. y3 e to the 1 cosine 2x. Yeah, we already did that earlier. And y4 e to the x sine of 2x. Put all of that together. C1 e to the 3x. C2 to C2. And then C3 e to the x cosine 2x. And C4 e to the x sine of 2x. Now, complementary solution, we have the constant, we have the e to the x cosine 2x, e to the x sine 2x, so all of this are complementary solution. So that means the form of particular solution is this. yeah, just write the constant. Right. Of course, if we have to guess, that would be a lot faster than doing all of this. But I said this is just another approach to solve the non-homogeneous equation, and it only works for the solution, the exact same function that we guess. So this is nothing new here. We still use the undetermined coefficient. We still have to do that to solve for the coefficient. But this time we get the form of the particular solution, a little more general, a little more elegant, come from the annihilator, which is the operator, differential operator. But other than that, the problem that we can work using the guessing method will be the same thing as the problem that we can work using the annihilator approach. Of course, if we want to work more type of function, then we have to use variation of parameters. But yeah, the nice thing about the annihilator is that we don't have to worry about the case where we have linearly independent. We have to multiply the x or x squared to it. It would take care of the problem naturally, and when we do this, it come out perfectly. That this is the new term, so that have to be particular solution. Right. Yeah. So the annihilator method, there will be less term to guess. Of course, we still need to know what we annihilate some type of function, but other than that, it will take care of itself. We don't have to worry about the case where we have linearly, do we have to multiply by x or x squared. It will take care by itself here. Right, with that I stop the video here. As always, thank you for watching, and see you in another video in differential equations.